Okay. Now, today what I am going to do is I'll have a slightly different style. I'll take up chapters 12 and now chapters 12 and 13 is basically JEE stuff, but we'll do a recap of it. So therefore, I'll be a bit fast, and the PPT PowerPoint presentation for these chapters for the book, actually I have also contributed to that. So therefore, for the dynamics part I have written and been a part of this whole group which made the PPT presentation. So 12 and 13 I'll mainly cover from the presentations. Normally I have been writing the lectures, but since this part is one which you may have already seen, so therefore I'll once in a while if I think there's something to be done, I'll come back to this, but otherwise I'll use the PPT. And maybe then if you find the PPTs are better, you can convey your feedback to me. Maybe then we can stick with the PPTs, and the PPTs I'll also put on my site, so that if you don't have to copy anything, the PPTs are mainly from the text from the book itself. Okay. So now the only one thing which I would like to say is that there is this concept of relative velocity and acceleration, which we have not seen. Let me just discuss this before I go to the PPT. So suppose we have a body A whose velocity and acceleration is known with respect to body B. Then, and we also assume that the body B is translating. So these are the two assumptions we have. Later on in the course, when we come to chapter 15, we will take up the general formula where the body B need not be translating. Now, what is the meaning of a translating body? Let us get that very clear. What would you say is the meaning of a translating body? Again, now that is exactly what he says, moving in a straight line. Now, and that is where I'll differ slightly. A translating body is one. If you fix your reference frame on that body, then this reference frame will not rotate, will not change its orientation, or not reference frame, I should say coordinate axis. If you fix coordinate axis on this body, then the frame with respect to which it is translating, in that with respect to that frame, the coordinate axis will not change the directions. So that does not preclude the body from moving in a curved path. For example, let us talk of a car. The car is translating even when it is moving in a curved path, it is not rotating. If it rotates, then I'll pray for you. So that is, so what we mean by translating is that any axis fixed to the body is not rotating. So it could move on a curved path also. For example, when you are on a Ferris wheel, this jhula which goes round, then you are not rotating. You are always in a vertical plane, and this Ferris wheel keeps on rotating. So a car may rotate, it may rotate, you are right, but then it could also but if you are fixed to the wheels, those they will change. Okay, so car was probably, the Ferris wheel is a better example. Okay, in a car, let's see if it is rotating the axis. No, axes are fixed, the car is moving. What I am talking of is if a particle or a body is moving. Yes, so well, so yeah, but in general you are right. So the car example was not probably the best example. So body B is translating. This implies axes fixed on body are not changing their orientation. So then in this case, what will happen is velocity of A will be equal to velocity of B plus velocity of A with respect to B. That means we know the body B is moving, the velocity of A is known with respect to body B. So, therefore, velocity of A will be equal to the velocity of B plus velocity of A as seen from B. So, this is velocity of A with respect to body B, and this will also, the formula also extends to acceleration, that acceleration of body A will be equal to acceleration of body B plus acceleration of A with respect to B. Okay. Now, but the key word is that this is valid only if the body B is translating. Otherwise, this has to be measured with respect to a translating frame. We will do the general formula later in chapter 15. So, right now this is easy to see, and one typical example which you may have seen where this is often used is when we talk of where do we need such things. We have a block placed on a triangular wedge, the wedge is placed on ground. Now, suppose the wedge is slipping down, or maybe I am pulling it up with a string, so it could have a motion. So, then the motion of B with respect to A, the direction of that is known, it is along the wedge. Okay. And the direction of velocity and acceleration of A has to be in the x axis, if I take x as the horizontal axis. So, now here if I make axis like this, then what I know is acceleration of B with respect to A or Vb with respect to A, this is down the incline, and acceleration of A or velocity of A, this is along the x axis. And why do we need things like this? If I am analyzing the motion of this, then by Newton's law we have discussed this, acceleration of B is equal to sum of all the forces acting on B, and acceleration of B has to be measured with respect to an inertial frame, which is a frame with respect to ground. Now, in this case I may know acceleration of B with respect to A. So, then I have to also then add to that acceleration of A, and suppose if this is sliding on the ground, let us say we have a case like this where it is given to us that the, let me draw this again, this is sliding down the ground, and this one, if we just leave it at rest, we will see this in the lecture later, but if I leave it at rest, if this starts to move down, then this will have to move backwards, and that comes from conservation of linear momentum, which we will be doing. But if that is the case, then what we have is that I know acceleration of B. So, the absolute acceleration of B will be a sum of this acceleration and a sum of this acceleration. So, it will be directed somewhere in between these two. You have to add these two, and that will give you the acceleration of B, and to that you will use Newton's law. There is another way of solving such problems, pseudo force, but that I will explain what pseudo force is, and we will come to that. Okay. So, this is how these things could be worked. So, now let us move on to, as I told you, we will start with chapter 12. While how do I move up or move down? Yes, ma'am. How do I move up? Does that know? Is there a okay? There is, I think, this one. Okay, let me just get familiar with this. Okay, that's fine, I think now. So, I'll, as I told you, some of these things I may even skip. So, in this chapter, chapter 12, we talk about forces, and we have already done a bit of it in the last class. Most of the things which are, so here basically the practical applications come when we talk of forces and when there are accelerations. See, for example, we are talking of a chair moving up a ramp, then all the forces acting on a wheelchair which come from the ramp have to be analyzed properly so that a proper ramp can be designed. Now, a big problem comes when we talk of swings, because in swings what we know is, what we have seen, that when something is moving in a circular path, then we have a v square upon radius of curvature. So, if the velocity is high and the radius of curvature is low, then an extremely high normal acceleration could come, for the presence of which the normal force has to act on the body. And in case like this, if it is a swing, then the normal force, if it is swinging like this, will have to come from the string, which means the tension in the string. So, and if that force exceeds the tension which the rope can take, the rope could break, leading to a disaster. So, therefore, we have to be careful, and we have to analyze all these things in detail. So, Newton's second law, which we have seen, sum of forces is equal to ma, and if the resultant force on a particle is not equal to 0, it has an acceleration. So, all this is something which is, so this we are applying to a single particle. Now, what do we mean by a particle? A body of a finite, very small size. Now, we apply this law to even big bodies. So, are we doing a correct thing? Well, when we apply to a big body, we are assuming that, well, either it is the center of mass, which will come when we talk of a system of particles, or we are assuming the whole big body behaves like a single particle. So, that modeling, what we say, is good enough for the purpose of that problem. So, then we assume the whole body to be a single particle. So, this is Newton's second law, and it must be expressed with respect to an inertial frame of reference. That is the most important thing, that the frame should not be accelerating, it should not be rotating, in general rotating frames, and this is for a constant mass system. In fact, variable mass systems we will not do in this course, where mass could be changing in a system, those problems will leave. Okay. So, now how do we work this out? So, if we replace this, basically the mass times acceleration is also related to the linear momentum. How do we define the linear momentum of a system? Mass times velocity. So, we have sum of all the forces is equal to mass times dv by dt. Mass being a constant, we can take it inside. So, therefore, what we get is d by dt of mv. mv is nothing but the momentum. So, therefore, in fact, some people define this as Newton's law. Change of linear momentum is equal to sum of force. So, either it is ma or linear momentum, you leave it. So, now when we have dl by dt is equal to sum of f. Now, if sum of forces is equal to 0, what does that mean? That dl by dt is 0. So, that is what gives rise to what is called the principle of conservation of linear momentum. So, now whenever we use conservation of linear momentum, you cannot use it if external forces are not equal to 0. Only when sum of external forces are equal to 0 will the change in momentum be 0. So, conservation laws, while they are treated as something very sacrosanct, but there is a condition. If sum of forces is not equal to 0, you cannot use conservation of linear momentum. Conservation will only come only when this left hand side is 0. Then dl by dt is 0, and therefore, L will be constant. Okay. Also, another thing we realize is this is a vector equation. So, we can even apply it on a single scalar component. If in x direction there are no forces, then the x momentum will be constant. Maybe y momentum will not be constant if forces are there, but because this is a vector equation, we can apply it along each component of this. So, again, these things which are there, you may have seen system of units. I will skip this. I think this is basically, we know the units of forces are newtons and mass is kilograms. Now, this is what I have done in the last class. If we go to Newton's second law, then we have sum of f is equal to ma. We write it in terms of the Cartesian coordinates first of all. So that means we are express the acceleration in terms of ax, ay and az. So what we'll have is sum of fx is equal to m times ax, sum of fy is equal to m times ay, sum of fz is equal to m times az, and that leads to this. Now, when is this form easy to use? This form would be easy to use if the forces are constant. That is one place where this form would be easy to use. Because if the forces are constant, then what I will get is mx double dot is equal to constant. I integrate that to get x as a function of time, y as a function of time, z as a function. So if I have constant forces, then this will be a useful form. Suppose if force is given to me as a function of velocity or as a function of distance, then this will not be so useful. I have to be careful. We have done these things. You write, suppose if this is given as a function of x dot, then you will put it as the function of x dot, and then x double dot you will have to write it as dv by dt, and there's a v, then you separate the variables and integrate. So you have to keep those tricks into mind. If this is given as a function of x, then what we will realize is we have another formulation of the same equation, the work energy formula, and that is what becomes easier, and we will see that. So, but this is the basic equation. The three, then if force is known as a function of time, then we'll integrate this. But that gives rise to another formulation which we call the impulse momentum form. Because what we do is we write fx is equal to m times dx dot by dt. And if x is a function of time, then what we do is we integrate this with time. So integral fx dt becomes m times change in the linear mode. And integral f dt is what we call will term as impulse. So these are the three formulations. So basically, one is the basic Newton's law, work energy, and impulse. These are the three formulations we'll be following. So, now, this is what I meant by pseudo force. And what happens is Newton's law is written as F is equal to M. If I take MA on the left hand side, then what do I get? Sum of forces minus MA is equal to 0. So now what one can do, and this is, you could call it as the engineers are very lazy people. So this was the engineer's way of trying to convert dynamics into statics. What we say is we can treat minus MA as another force, and then we say sum of all the forces is equal to 0. So this again became equation of statics. So this is, and this minus MA is what is referred to as either a pseudo force or an initial vector, as you may call it, or inertia force. So there are different names given to we have so minus MA is referred to as now. So this is what people refer to as then you say this is dynamic equilibrium. So it's equilibrium, but you treat it as a force. And see, for example, this you must have seen also in your high school physics when you talk of a body moving in a circular motion at, let's say, constant speed. Then there is a normal component of acceleration v square upon r. So mv square upon r with a minus sign will be acting outward, and that is what is referred to as the centrifugal force. Mv square upon r acting inwards is called the centripetal acceleration. Of course, the mistake you do is you use both together. That cannot be done. It is either the centrifugal force or the centripetal acceleration. So either you count it as acceleration or you count it as a force. If you count it as a force, then a minus sign has to come, and then you say sum of all the forces. So that is basically the concept of pseudo force. we'll see that how to extend this to other things also. So this is essentially the concept of dynamic. Now, in solving any problem, what one will do is, we have to draw the free body diagram, we have already seen this. And as the book refers to, the book also refers to what is called the kinetic diagram, where in addition to, you show a separate diagram and show the accelerations acting on the body. Or if there is an angular acceleration, they will be shown, and that will be referred to as the kinetic diagram. You don't need to do that. You've been solving problems probably without that, because that you do in your mind. So it's up to you whether you want to draw the kinetic diagram separately or not. But for example, let us say this is the block which is being pulled. The example which I was doing earlier, in this case the block is being pulled up with a force, the weights are doing. And here now, if you have to draw the free body diagram. So if you have to draw the free body diagram of the top body, what you will do is the force of 225 newtons which is acting, its weight acting downwards. Now because the block is being pulled up, the friction force will act on the downward side, and there is a normal. So these are all the forces which are acting. We have seen how to draw these free body diagrams. Only new thing now which will come is sum of all this must be equal to mass times acceleration. So that is what will come. Now, so as we do, if this has to be drawn, to draw the acceleration diagram, so we will write it as mass times acceleration. And how will this come out? Now in this case, because the body is moving on a wedge, we can't say the acceleration is just along minus x direction or plus x direction, it's moving up. Why does the y component of acceleration come? It will come because of the movement of the bottom wedge. So therefore, what we have to show is max and may. We have to keep in mind that these two accelerations are. So that is what we do, and that is how we will be able to do. So you don't need to draw the second diagram, which is being referred to as the kinetic diagram. But that is how. And then what you have is sum of f is equal to m. So that means everything which is in the x direction, sum of that must be equal to mx. Everything which is in this direction in the force, sum of all that must be equal to mx. Right? And this. So this is as simple as get. So therefore, we draw then there are some other problems. If you are supposed to draw a diagram of this system where you have a block which is moving up, there is a pulley, another pulley which is pulling it down, and it's pulling the lower block also. So now here, of course, assuming that all these pulleys are frictionless, then the tension will be the same. So you have to keep this in mind. And when you draw the free body diagram of this block, on the top block, you will have a tension acting upwards and other forces acting. And when you draw the free body diagram of the lower block, then you will separate it from this thing. So you will have, you will come in at this point and have a tension acting. So this is how. So we isolate the body. So that means we draw the lower block first point here, and then on this we show all the forces. So, see, for example, one mistake which people made in the minor, in problem number 2, was that there was an N-shaped block connected to a rod, and to which a string was there. And many people have solved the problem where they draw the free body diagram of the L-shaped body separately and of the horizontal body separately, and on both the bodies they show the string tension act. Now string tension had to act on only one of the two bodies, not on both, and therefore the answers would have come out wrong if you have showed it acting on both the bodies, because when you combine both of them, then the tension acts only on one of them, only a single tension. Whereas if you show it acting on both, and when you combine these two, you will get 2T, and that was the mistake. So similarly, there is another problem here. We have this rod on which a collar is moving, and we have draw the free body diagram and kinetic diagram for the column B. Assume that there is friction between the rod and the collar, and the motion is in the vertical plane and theta is increasing. So now, if you have to draw the free body diagram of this body, how will you draw? You isolate the body, then what forces will come from this rod on the collar? There will be a friction and a normal reaction. And what are the forces of this acting on itself? There is a weight. So all these are there, and that is how the free body. And now, if a problem like this has to be solved, what would be the convenient coordinate system to solve this? The cylindrical coordinate, because then you know the motion of the rod, that will be theta, so you can then solve things in terms of the cylinder. So let's see how he does it. He says isolate the body, you draw the body first, then you show the axis. So you show, because you use cylindrical coordinates, so you show ER as the outward direction, E theta as this, and then you will put your kinetic diagram, you will show the force diagram, you will put here, then you have an applied force. So then, okay, then you replace the supports with forces. So you show the forces, as I said, mg acting here, friction and normal reaction, and then dimensions, if there are any length etc. to be needed, you can keep that in mind. So you show, you put the angle theta there, and the kinetic diagram would basically consist of MAR and MAT. So this part, as I said, if you don't want to draw it, you don't have to draw, because you just say all the forces acting in this direction, whatever you have shown here, all the forces in the R direction, that will be equal to M times R double dot minus R. So then, I think some of these problems I'll skip. There's a block, 80 kg block resting on a plane, find the magnitude of the force required to move it. I think these are all quite simple problems in your. Then another problem is that when there are two blocks, then you have to relate their accelerations and the tensions, and then you can still work again. These problems you have done enough of left. And then this was the other one which I talked about, that we have a block rest, which starts on rest and stands on a 15 kg wedge. So the two masses are given, a block circle. Neglecting friction, determine the acceleration of the wedge and the acceleration of the block related to the. So friction is to be neglected here, that one is easy. We look at the solution, let's say. So now, if this has to move down, acceleration of A, first we draw the free body diagram of the body A. There is a normal reaction acting from the top, there is a normal reaction acting from the ground, and its weight. So this is the total free body diagram of this block. This must be equal to M times A. So we write the equation, we will get a relation between N1 and acceleration. N2 is equal to weight, that will come from the basically N2 minus N1. So we write the equations for Fx and Fy. How many unknowns will we have? We will, when we write these equations, we will have N1, N2, two unknowns, and a third unknown is acceleration of it. And what we will be able to get there will be only two equations. So just by writing the equation of this block, we will not be able to solve it. So we'll have to go to the free body diagram of this. Now here what will happen is, N1 is the same old unknown. Now in this, one unknown extra will come, acceleration of B with respect to A. Acceleration of A was already there as an unknown earlier. So now one more scalar unknown has come, its direction is known. And there will be, so now when we count, we totally have the required number of equations and unknowns. So which are the unknowns? Acceleration of A, acceleration of B with respect to A. Two scalars, N1 and N2, four scalars, and we have four equations. So here, writing this acceleration in this form helps, makes life easy, because acceleration of A is itself an unknown. So therefore you will write it in those terms and you will be able to. Of course, some of you may probably find it easier to solve by pseudo force, saying that we apply everything in to this block, and with this reference frame, then you will be able to get acceleration. So this is how you solve the problem. Now, and this again is another problem where 2 or 3 blocks are there. I think we can skip this because we have already. I think some of these concepts. Let's now try to see how we apply these things in normal and tangential form. So, and these sort of the new coordinate system which we have seen, the path coordinates or the circular coordinates, they are particularly useful in a lot of problems when you talk of a plane moving in a loop, or you talk of forces on the roller coaster as it is moving. So, what the normal direction which is coming, what the acceleration being experienced by people, that is very good. So, in path coordinates, when we apply Newton's law, so F is equal to F times, F is equal to ma. We write F as, I had done it last time, Ft plus Fne. So, therefore, what we get is acceleration. And sum of forces in the normal direction will be equal to mass times acceleration in the normal direction. Now, acceleration in the tangential direction is nothing but the rate of change of speed, dv by dt. And acceleration in the normal direction is b square by 1. So, therefore, we have this. So, whatever is the path, you write the et and en direction, and the forces in tangential direction will be equal to nt, forces in normal direction. So, and as I said, even if the body is moving in a circular path, instead of using cylindrical coordinates, you may prefer these. Because this is a very simple way of looking at this. That when something is moving on a path, the two components, the tangential component of acceleration is nothing but the rate of change of speed. The normal component is b square upon. And what we realize is that this component, actually this is the one which is sort of may not be very physical to see, because this will come even when speed is constant. So this is coming because of the change in direction. And this could be very large. If the speeds are large or if the radius of curvature is small, this component of force could be large. And that is why this becomes large. Now, as a usage of this, again, you may have seen this thing, but let's do one of the simple ways. If we look at a problem of the pendulum, so the length of the pendulum is given, it's 2 meters. It moves in a circle in a vertical plane, and the tension is given to be 2.5 times the weight for the position shown. So we have to find the velocity and acceleration at that. So how will we do? Once again, we'll start by drawing the free body diagram. So we'll draw the bob here. We show its free body diagram. What are the forces it will be? A tension and a weight. That's it. And at this position, wherever the position is, this will be the forces. So we'll resolve them along ER and D theta. Forces along the R direction will be m times R double dot minus R theta dot square. Forces along, and now here for this we will also realize for a pendulum R is constant. It's just a circular motion, so R dot will be 0, R double dot. So we just use either cylindrical coordinates or path coordinates. That's straightforward, and we will get our answer. So let's see. Resolve into tangential, solve the component equation, so we said that, and solve the velocity equation. Like this, we draw the free body diagram, we show the weight, we show the tension. In this case, tension is already given to be 2.5 mg, and that must be equal to these two things. And then, so we write it, when we solve the equation, acceleration in the tangential direction, this will be equal to AT. So it turns out to be nothing but g sin 30, and in the normal direction it will be, work out. So force in the normal direction is, we know the forces, we know 2.5 g minus mg cos 30, that must be equal to man. So this gives us the normal component of acceleration. Together these two, square root of that will give us the acceleration vector. How do we get the velocity? Velocity will come from here. An is equal to v square upon v. So once I know An, I will be able to do this. So I can do this. Of course, somebody will say I could use the work energy formulation. Then that would not have worked here because of the tension and all, but you have to, because the data given was in terms of tension. Now this is another standard problem where something is, the car is moving along a curved path and it is on a banked road. So I think there you know the equation comes tan theta is equal to this. I'll just slide this. Standard. Now this is one of the problems where we could use cylindrical coordinates. Here what is given is a 3 kg collar rests on a frictionless arm AA. The collar is held in place by the rope attached to the drum D and rotates about O in a horizontal plane. So this is all in a horizontal plane. It is in an XY plane. Okay. The linear velocity of the collar B is increasing according to the rate 0.2 t square. So this is the velocity which is in this direction. It is increasing as per this rate. And find the tension in the rope and the force of the bar on the collar. After 5 seconds, this R is equal to 0. So the data is given. You're asked to find the force and the tension in the rope. So you have the velocity, the speed which is going is given as a function of time, 0.2. So now, again we draw the free body diagram of the collar, then we will write the equations of motion, and then we will determine the dynamics. And combine these to get the formula. So let's first start by drawing the free body diagram of the collar. So on the collar, when I draw the free body diagram, there is a tension acting and there is a normal reaction which is coming from the rod on the arm. Why have I not shown any weight? Because this is moving in the horizontal plane. So there will be a vertical normal reaction which will be equal to the weight, which is taken care of in this. So it does not affect the motion. So that just ensures that it stays in the same. The normal reaction and the weight will just be balancing each other, and they don't come down. And this tension must be equal to MA and the normal reaction must be equal to MA. And that's it. Once we have this, then I think nothing too much more. So let's write the equations of motion. So sum of FAN, sum of forces in the normal direction, which is N, is equal to M times V square upon rho, and tension is equal to mass times acceleration in distance is equal to M. Now because V is known as a function of T, so therefore then everything is known. Time is given to you. So you this is at a fixed radius, so R is also given to you. So radius of curvature is known, V square. See, even though the body is moving in a circular path, what you should do is when you use cylindrical coordinates, try to think of path of the body. If it is a circle, then it is straightforward. Rho is nothing but R, and that's how. Yes. This corner is there, and this angle theta is changing. Basically, this rod is there, and this one, this whole thing is rotating. This rod is rotating, and the rate of change of velocity v is there, and this is in a horizontal. Now, these sort of things you could try, and I'll not do, but see here, a car is driving from A to B on a curved path shown. The driver is doing the following things at each point. At A, he is going at a constant speed. Okay. At B, he is stepping on the accelerator. That means velocity is increasing. At C, he is stepping on the brake. At D, he is stepping on the accelerator. So different things could be given, and you are asked to draw the approximate direction of the car's acceleration at each point. Now what will happen at, let's do one or two of these. What will happen at point A? There will be only, because he is doing it at a constant speed, that means tangential component will be 0. There will be just a normal component like this, towards the center. At B, it's a straight path, but he is stepping on the accelerator. So acceleration will be in the horizontal line from B to the right. At C, what is happening? at C, stepping on the brake. So that means the tangential component of acceleration will be upward, basically in that direction, and a normal component will again be toward the center. So the resultant will be somewhere like this. So this could be some sort of maybe not here, but often in a lot of competitive exams, etc. These type of things come as objective type of things. Now, JEE also, do you have things like this? Okay, so there could be things like this. So you are doing it a bit late. So these sort of scenarios are there. Now, this is trying to say where the cylindrical coordinates are. And cylindrical coordinates mainly are used when we have these coordinate actuators, etc. See, what you have in an actuator is something like a transistor antenna, that the thing is shifting out. There is a change of R, and at the same time, this is rotating. So that is where, if something is rotating about an axis, then cylindrical coordinates is definitely, and the real use comes when R is also changing. If R is constant, then path coordinates are useful because you know the radius of curvature. But if R is also changing and theta is changing, then cylindrical coordinates become useful. So these are some of the problems where you find cylindrical coordinates. And in cylindrical coordinates, basically, assuming we are talking of a plane, if z motion is there, then we get a third equation. So sum of forces in the r direction will be equal to m times r double dot minus r theta dot square, and f times theta dot square. Alternate shift calculation. Has everyone signed? So this is path coordinates, and now this is a similar problem as we had last time. But now the difference in this problem is that there is a radial component of the velocity of the block. In the previous problem, the block was kept fixed with a rope. Now, see, if you try to think in terms of number of variables, if the block is fixed with a rope, then the extra variable which comes is the force in the rope, the tension. If this is free to move, then the new variable will be the acceleration. So variables you will be able to solve will be, the number will be the same. If it is being constrained, then a force will come. And this we have seen when we did the free body diagrams. Anything which stops some motion causes a force or a torque. So that is what is happening here. Here we have cut that string. That's the difference between the last problem and this problem. If we have cut the string, that force has gone, but an extra acceleration. That's it. So now here a block B can slide freely on a frictionless arm moving, and it rotates in a horizontal plane. Again the same thing. Now the rate of rotation of the arm is given. So it's as before. Earlier the rate of rotation of arm was not given, d theta was given. Now here this is given that this is rotating at a constant rate, and what we are asked to find is the component VR and the magnitude of horizontal force exerted by B on the arm. So given these, let's try to see the solution. How? So once again, our strategy will be like this. We'll first write the equation of in R and theta form, and then we'll integrate the radial equation to find the expression for radial velocity, which is for r dot. And once we have that, then from there we will substitute that equation in the theta equation, because theta equation has r double dot. Once I know what is VR, which is r dot, the derivative of that will be my double dot, and then we will get that to find the force in the theta, which is the horizontal. So first, if I draw the free body diagram of the block, now there is only one force F, and this must be equal to the sum of these two. So when I do this, so the radial force is MAR is equal to MR double dot square. The radial force here, that is 0, and F theta. So now here from here what you get is R double dot will be equal to R theta dot square. So from here you know the expression for R double dot. Integrate that to get R dot, and that R dot can be fed here to get the value. That is because theta double dot is 0. So basically that is how the problem is. Okay, is that clear? So we look at the equation. So first we get to the radial equation r double dot, and we write it in a slightly different way, the work energy formulation type of way, that Vr dot r double dot is Vr dot. So that can be written as dVr by dt. So dVr by dr times dr by dt. So Vr dVr by dr. And therefore this can be written as r double dot is Vr dV. And r double dot dt, theta dot is constant. So basically what we will get is Vr square is equal to theta square times the r square basically. And from here you can substitute in the second equation. This expression for Vr square will be fed in, and from here we will be able to get. So now if this one, what's happening, another problem which I think we can probably skip, it's a similar thing. You have to just work out expressions for R. Now these are again some concept questions. A girl starts walking towards the outside of a spinning platform as shown in the figure. So that means this is a platform which is spinning, a person is standing there, and they start walking outward towards this direction. She is walking at a constant rate with respect to the platform. That means V is constant. And the platform itself is rotating at a constant rate. In which direction will the forces act on? So now we have to look at E1 and E2 directions, ER and D theta. Now if the question is, in which direction will the forces act? Among the E1 and E2 directions. So now force is what? Fr is equal to m times AR. So let's see. Forces in the radial direction. So just do this. Forces in the radial direction will be equal to m times r double dot minus r theta dot. Now r double dot is what? 0. Why? Because that is a constant velocity. So obviously, so that means forces in the radial direction will be only toward the center. So what direction will it be? So one of the answers should be minus E. Now what about in the E2 direction? Let's see. Will there be a force in the E2 direction? Because theta dot is given to be constant. So R alpha component is 0. Will there be a force in the theta direction? Now if you look at F theta will be equal to m times r theta double dot 2r dot theta. And here r dot is not 0 because there is a velocity, and theta dot is also not 0. So that means there will be a force acceleration first of all in the E2 direction, because r dot is positive and theta dot is also along this direction, omega is along that direction. So that means there will be a force, this because of acceleration some force has to be there, so there will be a force in the E2 direction. So the answer will be minus E1 and plus E2. Is that fine? I hope I did it correctly. So this is how. Now the other concept, I think I will now switch on to now let us discuss the concept of angular momentum of a particle. So, let us say a particle of mass m is moving with some velocity v. Then we define. So We define h about O. This is what we define as angular momentum about the point O. And we will also write it, some books call it moment of moment. Now, what is the momentum of this particle? M times v vector. What is the moment of momentum about point O? How do we find the moment? R cross this. So if this position vector, if this is R, then h about O, the angular momentum is defined as R cross and if this angle which the particle makes, the R vector makes with the x-axis is phi, then phi will be this one. So therefore, then what we will have is the angle. Sorry, phi will not be the same. Phi will be the angle between the R vector and the V vector. Then angular momentum about O will be equal to R cross MV or R MV times psi. So the angle between these two. Now, for plane motion, h about O will basically be h about O, the z component of this along. In plane motion, R will be along I and J, and the particle will also move along I and J. So when you take R cross MV, R will be along I and J, velocity also will be along I and J. So the only component of cross product which will be there will be along K. So that will be in the K direction, and this will be, can be written as M times X times Vy minus Y times. Now what we see is, then let's look at the rate of change of angle, HO dot. So this will be equal to d by dt of R cross M. So this will be equal to dr by dt cross mv plus R cross M times. Okay. Now dr by dt is nothing but v. So it will be v cross mv plus R cross some of the external forces. And from here what we get is this quantity v cross mv is 0. So therefore what we have is the rate of change of angular momentum is equal to R cross sum of forces F acting on the particle, and this is nothing but moment about. That is how we define moments about a point is sum of all the forces with respect to that origin. That's how we define moments. So therefore this gives a third formulation of Newton's law, that instead of writing things in terms of linear momentum and velocity, we can write sum of moments about a point O will be equal to the rate of change of angle. This is not a, as far as the single particle is concerned, this is not a new law. It is just following from Newton's law. We have used only Newton's second law to get this, and that is how this works. So therefore, now when we use this in polar coordinates, let us look at 2D motion of polar coordinates. Then what we have is velocity is equal to r dot dr plus r theta dot and the vector r is r here. So therefore now in this case when I take r cos mv, I will get r er crossed with r dot er plus r theta dot d theta is just equal to r theta dot. So if I have a so what we have is in polar coordinates for 2D problems, h about O is nothing but n r square. Okay. Now there are certain types of motion which take place when a body is moving under the influence of a force such that the force is always directed towards a fixed point in space. If the body is moving under the influence of a force such that the force is always directed to a fixed point, such a motion is what we call as a central force. So let me first try. Central force motion is if a body now in central force motion what we can do is that we can choose the origin as this fixed point and let us call this as O. So now the only force acting on the body is this force which is passing through O. So if this is the case, then what can I say about the angular momentum of this body? That h about O since F on the body always passes through O. So HO dot, which we said was equal to R cross NV, so that is equal to sum of all the moments. Now because we are taking moments about point O will always be 0. The force is always passing through O. So that means HO dot will be equal to 0, and for such a body H about O. So if a body is under the influence of a central force motion, its angular momentum about this point O will always be. So now if HO is constant, let's show some consequences of this. So what we have is the body is moving at any general point of its motion. R cross MV is defined as HO, but HO is constant. Now, if HO is constant, then what happens to, that means R the vector r has to be always perpendicular to h of, because by definition r cross mv is h of, but h about o is constant. So what the meaning of this? That r has to be along a plane, because HO vector is a constant vector. So r always has to be along this plane which is perpendicular to HO. If HO was changing, plane of r could change. But because HO is constant now, so r has to be in a plane which is perpendicular to HO. So that means a body which is moving in the influence of a central force necessarily has to move in a plane. It cannot move, it cannot have three-dimensional motion. It has to be having a motion in the plane which is perpendicular to it. So, body in central force motion has to move on plane, the plane is perpendicular. Now, and how will this plane be fixed? The plane is fixed by because h0 is equal to at the initial time t0, h0 will be r0 cross mp0. So whatever is its position vector at time 0 and the velocity at time 0, what is the plane between these two? That same plane has to be the plane of the body, and h0 will always be constant. Okay. Now, do we have any example of central force motion? Planetary motion. When a planet moves under the influence of a sun, or I'm calling of sun if I'm talking of a general planetary motion. If we talk of our solar system, then sun is it. All planets move around the sun. The gravitational force between two bodies is gmm upon r square. So maybe we can also write this. This again is something which you are probably familiar with. The gravitational force. We have a body of mass and another body of mass. And sometimes we write it as equal to minus gmm upon r square er, because er is pointing outwards and this force is pulling it towards each other. So now, if this is the sun and this is the planet always has a gravity. The only force the planet observes or it sees is a gravitational force which is directed toward the center of the sun. So as the planet moves in its path, it will this is a central force motion, so its angular momentum will be conserved above the sun. Okay. So now as this moves, so whatever path it takes, and here we can also then the angular velocity is r0 cross mv0. So this will be r times mv times sine of phi, where phi is the angle between r and v. So if this is the velocity v, this is r, the angle between them is phi, then r times m times v times sine of phi. This is what, because v sine phi will give the perpendicular component and times r. So this cross product will just become r times mv sin. So that must be constant for different positions. So this will be one of the equations you will get for the planetary motion from center. Now, if we, I think, in the next class, that's tomorrow, Monday's class, I'll talk about work energy formulation, and I'll also talk about the after work energy, the impulse momentum. These topics are